I'm going to start with a question that actually relates to a lot of what has been discussed before, but also by Natsuko and maybe is on more people's minds. But basically, Gaia BH1, Gaia BH2, and Gaia neutron star 1, which was discovered before, but it's all of these three systems seem to be challenging either the stability of mass transfer or how much common envelopes shrink the orbit. And let me run down the argument really quickly for those of you who are not known or not familiar with these systems. So basically Gaia BH1, BH2 are systems that were found by Karima Badri. They're all on orbits that are almost comfortable, that almost certainly make you think that the progenitor must have overflown its rush slope. So Gaia BH1 for sure is on about a 300 solar radius orbit. It's a 9 solar mass black hole with a 1 solar mass companion. A 9 solar mass black hole probably came from a maybe 30 solar mass progenitor. 30 solar mass progenitors become more than 1,000 solar radii big. 1,000 solar radii is bigger than 300 solar radii, so they must have interacted. For Gaia BH2, it's on the edge. You could assume some things where it didn't have to interact. And Gaia neutron star 1 might have come from a 20 solar mass progenitor. It's a bit more difficult with neutron stars, obviously, to really see what the progenitor mass was. But the same argument holds. 20 solar mass star becomes bigger than 500 solar radii in most cases, in almost most conventional stellar astrophysics. So then the question becomes, if they did interact, and you have the situation of this 1 solar mass companion in all three cases-ish, plus a 20 to 30 solar mass donor, then how you would expect that to go unstable because it's 20 to 1 or 30 to 1 mass ratio. However, if it wasn't stable and you go into a common envelope, why are they still so wide? So basically these questions, there's three solutions to these questions. This first one is they didn't go into unstable mass transfer at all. And you can go do stable mass transfer out to mass ratios of 20 to 1 or 30 to 1. That's pretty wild, but we have a lot of experts in the room. So I want to say, my question is, how wild is it? Option 2 is common envelopes don't actually shrink your orbit, which is what's the difference between a common envelope and the stable mass transfer at that point? And option 3 is none of these came from isolated binary evolution, but I would have to argue there are arguments for saying that these should come from isolated binary, and they are also probably very common. These things are probably not outliers, but rather the rule. So I would love to talk more about this with other people, and I would love to hear anyone's input.
Thoughts, questions, comments?
For the case of the neutron star, could it be just like the kick from the supernova?
Yeah, it could be, but this particular one has an eccentricity of about 0.1. So they actually argue very clearly in the paper why they think it shouldn't be kicked much. They even constrain on how much Blau kick they could have gotten. So this particular case, I don't think the kick will have helped.
Thank you.
So I guess a comment, we were having this black hole meeting in the Lawrence Center a year ago, and I guess another possibility, very speculative, is that maybe they never interacted.
Yeah.
So maybe the black hole just formed and never expanded. It might have lost mass and go straight to be a Wolf-Rayet.
I agree with that, but then you would have to say that for all of these. So that also implies that most stars don't become that big. And especially for the neutron star, I think they have a section in the paper as well, arguing could the low metallicity of this system prevent interaction. And they say, or keep it as small. And they say you'd have to keep it smaller than 50 radii to never have it, solar radii to never have it over interact. And they say that's unlikely.
Yeah, for sure. The neutron star is quite tricky.
Yeah, but good point.
I think one more. Yeah. Tomer?
Just a question. You mentioned that there are strong indications that these are
formed from isolated binary evolution, or some of them are? So
Yeah.
can you reiterate what these arguments are?
Yeah, so that's a hot topic. So I think there's definitely people who would disagree with me. But so for the neutron stars, the argument is mainly the low eccentricity. Would say if you have it formed in a cluster, you would expect some higher eccentricity. For the other two, it's a bit questionable still. For the BH2, you could say more comfortably, maybe it formed through isolated binary without ever interacting, because you don't have to stay that small. And for Gaia BH1, there's actually some papers out there that say, okay, with cluster formation, you can form it. But in my opinion, there's still problems there, because in the cluster formation, you need a common envelope to still form these systems, which to me is a red flag of, okay, if we still need a common envelope, even in a cluster formation scenario, then why do we have to go through all of the bother of the the cluster formation? But I'd love to discuss about this more. Okay,
Great.
next person, I think.
Next, yeah. Oh, one more quick question from Hongwei.
I personally think it's possible we can study it from the theoretical point of view. Like one is that if they undergo common envelope evolution, for example, the progenitor, the previous evolution, they may either loss of the envelope, so the binding energy would be quite different from the previous belief, or after the common envelope, there might be a thick envelope left. So the binding energy will also be different, but that's something we can check actually.
Yeah, yeah.
And then one more quick one from Sophia.
Yeah, well, coming from me, you may expect this question, but then how about triples?
Yeah.
Many of us-
Good point.
I promised myself I would not be the crazy person in the room that would always ask how about triples, but
It's
yeah,
no,
so
it's
important.
fair. Maybe that's the solution. All of these were in triples. I don't know.
But there's consequences about that, right? Because this could, I mean, you would still have mass transfer in a triple. It could, if that third star is far away, it wouldn't be different from a binary, right? So just saying triples solve everything, let's not do that. So, but then the only thing I can come up with is maybe an inner binary that's transferring mass, the orbit widens, and at some point you run into that third star. But that means that this mass transfer would have been halted halfway. So maybe you would have a star that's even less stripped than the non-stripped stars we already have at the low metallicity. So could that provide us something? Like, would these black holes, neutron stars look any way different if we only have stripped them?
Yeah, I think whatever we come up with, whether it's through triples or altered mass transfer, it has to be common. It shouldn't be the exception, which I think is possible for this. But
I mean, mass transfer is common in binaries, mass transfer is
Yeah.
common in triples.
but the mass
Stars
transfer we
gonna
have right
be
now
in
doesn't work.
places, So I think running into your third star is.
Okay.
Why do you say it has to be common?
So I think the argument is that if you have these two now, in DR4 they expect to see hundreds. Because they only probe a small volume now because there are strong mass cuts on the data DR3.
When you observe an object for the first time, you pick the oddballs.
Okay.
You what? Sorry?
Pick the oddballs. When you're
Oh, you pick the oddballs. Yeah. Okay.
I think I'm gonna have to cut this this off.
Okay.
For the sake of time, this is slide one of many.
Yes.
All right.
Okay. Mathieu, go
That's
next.
me. I can.
Mathieu?
Okay. Yeah. So my question is a theoretical question that relates mostly to after the mass transfer, but also to the stability at the beginning, because we heard this morning that it's important to take care of this thermal timescale mass transfer phase that is initially stable and then maybe leads to an instability. But we have been discussing only about the donor star here, but in every binary there are two stars, and the accretor also reacts to the mass transfer. And the way we treat this reaction in 1D code is, in my opinion, very ad hoc. We typically most people are in this part. So they assume that the accretor will be spun up by mass transfer, reach critical rotation, and at so this is a plot of the mass transfer rate as a function of time for a particular system. As the star spins up, it reaches critical rotation, and this balances out the mass that is coming in from the Roche lobe. And then we get this evolutionary behavior where we have the star spins down a bit, spins up to critical, stops accreting, spins down a bit, then accretes again. And this doesn't look necessarily very physical, or maybe it's something that we could probe with observations. And from 30 years ago, we have alternative models that assume some coupling between the star, the accretor star, and the disk that can allow for angular momentum to flow out and mass to continue flowing in. And in this group of models, you could have that the accretion rate basically might not care about the rotation rate of the star. And this can influence the radial evolution of the accretor and therefore the stability of mass transfer, because if the accretor also starts filling its Roche lobe, maybe we shouldn't call that a stable mass transfer. It's definitely not the vanilla mass transfer again. And so how do we make progress? Like right now, most of us, I think, sit in here. How do we address this?
So I just want to quickly say that I have a session on that tomorrow morning. So there's going to be more information potentially to drive a discussion with that.
Okay, great.
Ruger is on
We
deck.
can go defer this to tomorrow. Let's check with that.
Thank you. So I agree with everything you said. I think it's very important to understand this. And yeah, my question is maybe for the observers, if you think that there could be some observational constraints on this, because from the theory side, I feel a bit that we can come up with many models, but it's very difficult to tell which one is the correct one. So I don't know if we have some hopes from the observational side to understand this.
Hi. So I would say one of the observational candidates that we can use to investigate how much of the, basically this will create a dependence on the mass transfer efficiency with the orbital period of the binaries. And so we have the algols, the accretors of the algols, which we can characterize very well. And if you look at the mass ratio of the algols as a function of the orbital period, if you have high mass ratio algols at high orbital periods, then you probably have a high mass transfer efficiency at higher periods. And then you have to have this kind of a disk star coupling to allow for more mass to be accreted by the accretor, even if it reaches critical rotation.
The complication is that usually brings in tides, which is another whole field that we don't understand very well. But yeah, definitely, I agree.
Yeah, I want to maybe make a comments for low mass star n. We observe the exactly same thing. Let's say we turn on angular momentum transfer, while mass transfer, the accretor star will quickly spin to the critical rotation rate and then have this enhancement. So that makes our mass transfer efficiency super low. And also we also in our most recent work, we also trying to turn magnetic braking on, which is very efficient to spinning down the low mass star. If the star has a convective envelope. It's still not quite efficient to spin that down. Just additional comments, the mass transfer efficiency is still very efficient. So leading to very non-conservative mass transfer for low mass star world.
One last quick question.
Yeah, I just heard the alarms. Well, I'll be quick. I'll talk a bit about it tomorrow, but I do think indeed we need more, because if you don't, we expect from our simulations that there will be this matter flowing around your binary. So you have to accrete more matter, because otherwise I guess we would observe these things, or you would have a lot more mergers happening.
Do we know that we don't observe?
That's a good question. I don't know.
Okay, next slide. Thank you.
Katie?
Yeah, I'm in the back corner, which is quite annoying.
Yeah, just go here. Okay. I think this
So full disclosure, I put this slide in before not supposed to. So this is something that's been freaking me out as an isolated binary person. And I just wanted to like first get the temperature on the room on whether or not these intermediate mass high eccentricity things, if anyone does think that you can make them all through triples and clusters, do you think all triples and clusters, Sylvia?
No.
No. Okay, that's what I was like, wow, I'm a little surprised. Yeah.
I don't want to interrupt what you're
No, you're good.
saying, but I think the problem is much wider than just these white dwarf main sequence. You see it in barium stars, you see it in carbon enhanced metal core stars, you see it in the post-AGB stars,
Also the SDBs.
SDB stars, the blue stragglers are showing it. As far as I know, every binary population in this period range that shows some sign of being post-mass transfer shows this behavior, shows these eccentricities. So can triples make these binaries? Yeah, they can make eccentric
Sometimes.
sources, but I think this is so efficient. I'm sorry, but binaries here do something as well, especially because most of these populations are for the low mass part, where triples are less abundant than binaries. So, sorry, I think we're missing something for
Yeah,
binaries.
good. Okay, love that. I love to be told that triples can't make everything. The next thing, so
I don't
as
know.
a-
I said triples can do this.
No,
right?
just not all of them, not all of them. That's what, sorry, I said it wrong. The next thing though, so I'm in the business of trying to put this stuff in code, and we've been dragging our feet on eccentric mass transfer in cosmic because every time you talk about doing eccentric mass transfer, people say, oh, well, the only models for which you can do this are totally conservative. So, which I think like, yes, it's probably a problem. Is this something that is enough of a problem that we need to do something different before we try to put eccentric mass transfer into the rapid pop synth code? Like, is it worth trying that? Like, but that's kind of where I'm at right now. I'm very like, ugh, like, I don't know what to do because it's going to be a lot of work to put that into the rapid pop synth codes. And if we put, like, if I bring a beautiful second year grad student into my group and say, do this, and then it's like, guess what? It doesn't work. Like, I'm going to feel like a really bad person. So I would just like to like not start better. Yeah.
Maybe one thing that can be a motivation to instead go in that direction is that at these periods, we don't expect tides to do much. No, but then you would end up with very non-conservative by default.
think,
And
yeah.
that's the opposite of what you have. Never mind.
Yeah. No worries. Sylvia.
Yeah, I wonder a little bit what you mean with eccentric mass transfer, because with triples, when we use that term, we mean systems that start in an eccentric orbit. So here, I don't know if that's the case. I mean, that's something that we can discuss this afternoon, because most of the scenarios that I know that have looked in this problem, they talk about eccentricity pumping mechanisms that occur afterwards, right? And then there's not so much of a problem because your star is, you know, in such a wide orbit and tides are not doing anything anymore. But that's a different scenario. And I think, as you say, like most methodologies that does simulate eccentric mass transfer, it's conservative, but it's also only valid for extreme mass ratios above 10, which is also not
I think that's
system. So it's severely limited.
Yeah, you're giving a much more beautiful, eloquent version of my concerns, I think, which is because like if we look at just initial condition distributions, like main sequence populations, they are eccentric, they are in wide periods. Like, so we do know that we have a very wide range of Roche overflow conditions. And that's my fear with these like the mass pumping mechanisms. Like I'm literally thinking of like Adrian Hammer's code because he wrote it and is public. And so it's like, yeah, chuck it in, but I don't know that that's actually like the right way to move forward.
It's probably not. I used to work with
Yeah.
Adrian and he was pretty dubious of it, but it's better than nothing. And I
Yeah.
do also have one other comment to make about these eccentric mass transfer systems, about the onset of mass transfer in binaries. So I think there should be,
So I think the onset of eccentricity, or the eccentricity at the onset of mass transfer, even in binaries, is like probably actually relatively common. So tides are pretty inefficient as a process. And unless your stars are low mass and have deep convective envelopes, then it's actually pretty difficult to circularize systems quickly. So I think that this is going to be, I think it's really important.
And I was wondering if the rapid population synthesis models have wind mass transfer in there and what prescription they use for that, because I think that's another big area that could be improved. The people that have included it in smaller studies have found that it does improve the situation. It doesn't solve all the problems, but it does help.
I would say yes, but not great. At least in cosmic, but yeah, would love to chat about that.
All right, thank you, Katie. Next. All right, Nikolai.
Yeah. Yeah, whichever you want.
Okay, just to answer the previous question about can observations help us in something, I have some hope. Let's see. So we have kind of a lot. I wrote here a lot. A lot means free. But they're not synchronized and the crater is fast rotating, not in this system. So here is just a HR diagram with kind of well-known algal, one of the algal, and where already I made some attempt to, to feed them to the, some of the MESA model which are available with conservative mass transfer, and kind of for the primary and secondary. And on this diagram, I'm showing the evolution of the surface rotational velocity, because one of the constraints will be, and like, as I mean, we already mentioned it, that how to treat mass transfer during, I mean, in terms of critical rotation, because very fast we can reach it, like on this green model, and on the top, it's like how the evolution of the critical rotation. So it's really going down since the star is evolving. And okay, we can really fit it on the HR diagram, but what to do in terms of rotation? Okay, it's not that fast rotator, but we do have some examples where we have like VCNI of 300 meters per second. But I mean, what to do actually here? I mean, should we really care about rotation, or we should forget, or we just need to fit on the HR diagram plus period? Because also the period for such system is like less than 5 days. It's like 3.6 or something. And I can't reach it so far. I can't really, it's, I mean, or my models are not that good, but I mean, so the question is, yeah, I mean, from where we need to start in order to constrain.
Yeah, thank you. So you said you have 3 systems non-synchronized below 5 days.
Yeah.
Okay.
7.
Because yeah, I know about maybe 10, 15 systems that are maybe between 12 days and 5 days or something like that. And they are non-synchronized. But what is puzzling me is that they are not rotating a critical rotation. This is the thing that is weird for me, because as Mathieu said, you should, if you start accreting on a star, you should get critical very fast. And I'm also very surprised to hear that apparently magnetic braking cannot slow down the star enough. So I really don't understand how can you have something that is non-synchronized, but at the same time non-critical during mass transfer. I'm talking about algals, of course.
The other slide, I have a other slide.
You have a slide. Next one.
No, others going all the way back.
Okay, wait. But is there another question?
No, it's a plot, I think, which is relevant to this discussion. Yeah,
This
that
one?
Yeah. So if you look at the right side plot, so this one shows the super synchronicity of accretors during slow KSA mass transfer. So this is basically the algals, and the different colors show the initial orbital periods. So if you look at like 2.4 days and above, you can have like super synchronous rotators, and quite a handful of them. And it of course
After
depends
from
on,
the very slow, very small periods.
yeah,
They're widening. Okay.
yeah. But like if you start already from like a 2.2 day orbit, you can get an accretor which is not like rotating synchronously.
I think we need to move on to.
Put more questions on the Slack or Connect, and we will have group discussions on Wednesday as well. So this is really meant as a starter. Let me go to the next one, which is it is you, Kurtik. So
So then carry on.
yes.
Hi. So this is something I like found out about algols like really late into my like PhD, and I don't have an answer or an idea of how to deal with any of this. So these are called double periodic variables. So these are semi-detached systems, which in addition to having an orbital period, which is of the order of 1 to 10 days, they also have a super orbital period, which is 33 times the orbital period of the algols. And if you look at the like ratio of this super orbital period to the orbital period of the algols, they are around 20 to 30 or 30 to 40 times. And this seems to be consistent with like all the like throughout the orbital period range of these semi-detached systems. So yeah, and there are some ideas in the literature, but like there is no current consensus on how to like explain this. Like really, like there are already like hundreds of these systems observed in all three, like in the Milky Way, LMC, and SMC combined.
Interesting. Any questions about these double periodic variables?
Do we know that the variability, once you remove the orbits, is related to binarity? Because in the SMC, there is like a crazy OE star that is claimed to be in a very eccentric binary, possibly with a compact object, etc. But that shows a 30-day period variability that we cannot explain. And that one should have a period of years or more. So my hunch is that in that particular system, the variability is intrinsic to that star, which may be a product of binary evolution. Could that also apply here? That is something related to the star that you're seeing that dominates the light intrinsically.
Yeah, but then there is also numbers, right? Like there are like a lot more of these, like there are more than 100 of these observed. And like, are all of them, like, can all of them be explained by OE variability, especially in the galaxy?
I guess, do you find any stars with similar variabilities that are not in binaries to test if it's a single star process?
Like, I don't have any idea. Like, this is just a question that I have. Yeah.
I just wanted to comment on you. So intrinsic variability is related to the dynamical timescale of a star. But if here the period is 30 times larger than the orbital period, and the dynamical timescale of a star is always a little bit less than the orbital period, so they cannot be related. If the second period is 30 times longer than the orbital period, then it cannot be related to the intrinsic timescale because it's 30 times longer than the intrinsic dynamical timescale.
Yeah. Also, like to longer periods, you have an infinite order of G modes. Sorry, to lower periods, you have an infinite run of G modes, right? And those are the things that would couple because you have your L equal to quadruple mode. That's exactly what you would expect from G modes. Sorry, that was just a small
I feel
comment.
like not everyone in the room can hear. Is there a question on that side?
Comment from Evie.
Yeah, this is probably wrong, but I was thinking pulsations. It's just what popped in my head. You suggested that it could be pulsations, but you said these are these like main sequence stars,
Yeah.
and they're B stars. So
Yeah.
maybe not. I was thinking more inflated
Yeah,
envelopes.
and I think this Desmet 2010, this paper like investigated the first two ideas, and they basically concluded that these cannot explain all of these.
Could these be like BE like the BE binaries? You know, having these decretion disks on a periodic time scale that's kind of excited by the companion?
Yeah, that is one of the like ideas, but one of the things is like, does it always be like will the ratio always come to like 30? Like we have to have a mechanism that would like make the ratio around 30 for all of them.
No, we have time. Jared?
I think we do.
Okay, next slide. Thank you. Ruggiero, yes.
Yeah, so we talk a lot about mass transfer efficiency, so how much mass we lose during mass transfer. But I think a complementary, maybe equally important question is how do we lose this mass? So I've written here some options, as I'm sure there are many others. So do we lose it from the accretor fast twins, as many people assume with the 1D codes, or do we lose it from outflows from the Lagrangian point close to the accretor, from the donor, or from a hotspot, or other ways? So I think that if we want to understand, for instance, the huge variability of mass transfer efficiency that seems to be inherent in the mass transfer systems that we observe, sometimes they're very conservative, sometimes they're very little conservativeness. And so maybe this is something that we should try to understand, because some of these mechanisms may work for some systems or in some phases of the mass transfer, and some others may work in other phases. And so if there are several ways to lose mass, this could be a key to have the variability that we observe in the mass transfer efficiency of the systems.
Next question, comment?
Hi, Monica Gallegos Garcia. I know this is a diagram, but I think the one not listed here is mass loss from winds from the surface of the accretion disk.
Yeah,
so they are seen in X-ray binary systems, where they see outflows sort of from the outer edges of the disk, which will have different angular momentum than what we're currently assuming with isotropic winds from the accretor.
Thank you. Any other questions, comments? All right, next. Oh.
I guess it's just like, I would be curious, like, to also discuss, like, I think it's a very interesting topic, but also to discuss this topic, like maybe with people, like, how much can X-ray binaries tell us about this?
Maybe
I'd be curious
the
about your thoughts.
Yeah, maybe the mechanism that happens during X-ray binaries is totally different from what we have during main sequence star mass transfer, for instance.
I'd be curious.
Next slide. Next.
Okay, thank you. Well, category figures. Jan Fei. You can stay there if you want, whatever you want.
Okay, yeah, I think here I just want to mention that we heard all the uncertainties from 1D models. I truly believe that the way to actually at least improve some of the issues go 3D, and particularly if you want to go 3D with the radiation hydro. Here I just want to show some examples of what we can do now to study some of the issue of mass transfer in binaries. We have also fully resolved the 3D radiation hydro simulations on the outer part of the kinematic star in the reservoir giant. Here is the example about 13 solar mass. And then if you put another companion like 9 solar mass with a different separation like 2000 or 4000, you can actually now study in 3D the outcome, how the mass start to transfer from the surface of the reservoir giant all the way to the equator. Then, for example, we heard all the talk, people assume like isothermal adiabatic in 1D calculations. Here, you do not really need to assume that. And in reality, the system is neither isothermal or neither full adiabatic, because when you're actually near the photosphere, the radiation transport will actually determine the thermodynamics of the stream so consistently. When the system is closer, for example, the stream will be thicker, and then you will definitely the cooling is less strong. If you move further away and the stream is thinner, the property is also very different. So, and then you can also study the effect of the fully resolved convection, how that respond in the binary system. At least preliminary, the system definitely not unstable as you will usually think for the kinetic case. So I think really the motivated questions that for people do 1D models, where you can really run a few 3D ones, like what are the most important questions? Like what are number one, number two questions that you hope we can at least understand better in terms of the binary evolution?
I was trying to give time to other people because I kind of involved here. But in both of these models, actually, you already have the flow of matter in the envelope of the donor. Can you say already from these two preliminary runs if the matter goes around equipotentials or across equipotentials?
Yeah, this movie is actually the iso surface for a particular density. If you see, if they have a density cut, the four simulations have material actually in the outer part of the binary together, but the amount of mass you get there is actually very small, so it's not included in the figure. But there is also a question in the timescales. So the simulation in 3D can really resolve a relatively short time scale. So I think that is still a uncertainty if what happened in the long time scales. So I think the value of those 3D simulations is using the relatively short time scale to constrain some of the process and see whether you can improve and also remove some of the uncertainties in 1D.
Because I don't work on like hydro simulation, my question might be very naive. Just based on my understanding of like hydro simulation, is really challenging. Let's say for this case, the star size of the star could be like way smaller than the accretion disk. So that may challenge the hydro simulations. So I'm wondering, this is for like red supergiant accrete onto another massive star. Like how far away from, like, let's say we simulate something similar, but like focusing on low mass binaries. But like the star size and compare with the disk size could be even huge. Like
yeah, I think the scale separation is always changing. That's why we chose the parameters, because the other parameters are easier to do in full 3D, and that is doable now with the current resource. But if you want to go low mass, you have to design your 3D simulations, focus on a particular part of the problem, definitely not try to include the whole system together. For example, you can just resolve on near the surface of the low mass star, but try not to include the companion in your grid. You can still answer some of the important questions. But just even with the current computer time, do full 3D radiation hydro, still not possible if you try to do the full system for low mass stars.
No, I think I have a question. Oh no, is there a question on that side? You have priority.
I know that in 3D codes, time is always of the essence, and especially here, are we looking at a steady state, or is this the very beginning of mass transfer, so to speak?
Yeah, the time scale we can do is at least a few binary orbits, and for each individual one, we recover many thermal time scales for the rest of the giant. The reason we chose the rest of the giant because the thermal time scale is actually not that long compared to the thermal time scale. So this is more or less actually in the steady state. But if you really want to see the change of the mass because of the accretion, then that will be far beyond. So this is for fixed potential and see what is the steady state flow properties.
All right. I think next slide.
Yes.
Bethany.
Hi, I'm Bethany from the University of Toronto. It's nice to see you all. And I wanted to highlight some recent work that came out. During my PhD, I worked on building this UV catalog of the Magellanic Clouds with the purpose of finding strip stars, like massive stars post-interaction. And from that catalog, we found hundreds of strip star candidates, and we picked a subset of those, and we went and got optical spectroscopy, like one at a time, and confirmed like a handful of them as actual strip stars. We have since switched to using a multi-fiber spectroscope, and we've gotten some data that's been reduced and cleaned, and we expect to have a lot more strip stars coming shortly. And we're also working on characterizing these systems. Like the plot on the right is a system with a strip star and a compact object in a very tight, like 4-hour binary. And we also see indications of things like ellipsoidal modulation that follows the orbit. So we are kind of up to our eyeballs. I have a student that recently joined us, Alex LaRoche, which will talk more about some other systems. But we have a lot of like observations of strip stars. And what I'm really interested in learning about is how we can use those to constrain some uncertain parameters associated with mass transfer and the stability of it and things like that.
Thank you. Questions, comments, ideas? How do you precisely define that your sample is actually post-interaction?
Yeah, so do you mean like before we confirm it, or just you mean from the photometry?
Whatever, you know.
Like how we identify the candidates or to confirm them?
No, confirmation.
Confirmation comes, we find optical spectroscopic follow-up where we see indications of helium-2 and little to no hydrogen.
Yeah, all right. Do you have spectroscopic follow-up for like the majority of your sample?
Yeah, so we have the ones for that are on this plot here, and then like we have a multi-fiber data coming in soon. So we do have a good majority of them coming.
Yeah, I'll ask that question quick. So do you have like statistics on this population in the sense of like what the rate or how common these systems are, say in LMC, SMC, like intrinsically, or is it hard with observation bias?
Yeah, so that's actually like a big component of like my postdoc proposal is to like look into like the binary fraction of like the LMC and SMC using these observations. So hopefully soon.
Just a stupid question from a theorist. So you, as a follow-up question to what you just said before, so you just essentially, to define a post-interaction massive star, you say low hydrogen, high helium, right? But how do you discriminate them, for instance, WNH?
Discriminate from what?
Like from WNH, for instance. I mean, how do we know that, for instance, it's not because of wind that we get like
those would, yeah, so like the W and SARs are on this plot like as the purple diamonds, and they're just like so much brighter.
Okay.
Spectroscopy spectral lines would be completely
okay.
Yeah,
because it's broader.
No, it's an emission. There's a emission.
Okay, sorry. Okay.
Yeah, there's the plot that shows like a WN or WR spectra compared to ours in this paper where this plot is from, and I can show you, and it's like they are very different.
Just one quick question. Did you see any pulsations in the photometric flux?
So Cole can actually talk about that.
Well, it's a great question. We're making predictions for this, and I have to apologize to everyone who's involved for being slow and writing up the paper. I can show plots about it. Really fun predictions. We went hunting for pulsations in the sample, and that's where we have that light curve from up there. Unfortunately, we didn't find anything this go, but we only looked at 3 stars. So I think we're going to ask for more time and look at more stars.
All right, thank you. Next slide.
Oh, you had a second slide with me. Anna?
Hi, Alex had a slide. It's
oh, sorry. Oh, sorry. It's the same.
Yes, it is the same because it's the same sample except a different kind. So Bethany just talked about a strip star with a compact object, and I've been focusing on a subset of these strip stars, which are sp2s, in which you have spectral lines, helium lines coming from the strip star, but also Balmer lines coming from the B-type main sequence companion. And these systems are really interesting because we know that they're post-mass transfer. So by studying the properties of both the donor, the strip star, and the accretor, the B star, we can attempt to better understand both mass transfer stability and efficiency. So here I'm highlighting star number 9, the one in a circle there. So This system seems to currently have a mass ratio around unity, in which there is a 2 solar mass trip star and a 2 solar mass companion. And we think that the system pretty much underwent fully non-conservative mass transfer, in which none of the envelope made it onto the companion, which implies that this system had an initial mass ratio, which is basically intersecting the mass transfer stability boundary between common envelope and stable mass transfer. And furthermore, we seem to be finding that the accretor has actually been perturbed through this mass transfer process. So on the bottom, I'm showing Balmer lines there. The green line is a model where we're including the contribution of a B star, and you can see that the observed spectra in black is a lot narrower than the B star model would suggest. And we think this means that the B star is actually getting puffed up through this mass transfer process. And additionally, we've also had some preliminary results for other types of these systems, other sp2 strip stars, and we seem to see that 3 other systems are also lying on the mass transfer stability boundary. So we're hoping that we can use these systems to constrain efficiency and stability in general. Oh yeah, yeah. Well,
Okay, it's Tomer. Yeah, this is super cool work. I was just curious. So can you do this with all the stars?
Yes, eventually. It'll take some time, but I think, what is it, 7 or 8 of them are of this type. So not all of them, but a significant quantity we can get constraints on both the donut and the accretor, yeah.
Maybe it's a bit technical and we can discuss this later, but you said that compared to your model, it seems like your B-type stars are a bit puffy or lower log G or something like that. But do you account here for light dilution, like the fact that the flux of the B star is diluted by the companion?
Yeah, so we're accounting for the flux ratio issue here. So we're actually combining SCDs in a way where I think that's your question, right? Yeah. Okay. So on the technical side of things, what we're doing is that we first try to get a handle on the properties of the strip star by only fitting the helium lines, which you know are strip star dominated. And then after that, we fold in the SCD of the B star and then try to perform this whole analysis in a consistent way, hopefully.
I have one other question. So you say that you can constrain basically whether or not mass transfer was conservative here. What I would ask is, how dependent is this on other assumptions in the models like angular momentum, loss, and so on? Because it's amazing if you can constrain the stability of the conservativeness of mass transfer, but then there is a plethora of other parameters that can sort of ruin this. I don't want to be very skeptic about this, but I'm always very concerned on the assumptions in the models that you put here.
Yeah, so for example, I mean, there is definitely a metallicity dependence, the amount of stripping that you're getting, and we do have to assume the metallicity in LMC, for example, whether or not that's correct, you know, who knows? Yeah, I would say that this does rely on us making assumptions about the model grid that we're using, and that should be a caveat to our results here.
One more on this.
Yeah, with this observational sample, with this magnitude curve, do you know how complete this sample is? This sample of stripped helium stars in LMC, for example, is it fully complete, or how much % do you expect this to be complete?
I'm going to defer to Bethany on this one.
Can you repeat the question? How complete is this sample of stripped helium stars in SMC and LMC above this mass curve?
Yeah, so on the plot, like that goes in apparent to about like 19th magnitude. So there are some like limits on like the brightness that we can do. Another limit is like clustering, because like the reason this hasn't been done before is because clustering is very hard. So like those are a couple things, but the completeness is going to be assessed more when we do the population part of the study.
All right, thank you.
We're going to move on, and to speed up efficiency, can I ask the person who has a slide to come up so we don't have to move around as many with the mics? Can you come up here, Anna?
Sure.
And then if you know your slide is next, be prepared to come over here.
Hello, everyone. My name's Anna Lamb. I'm a master's student and I'm working with Floor. We are interested in gravitational wave sources. However, I've kind of fallen down a rabbit hole of wondering what happens to binary systems that don't become double compact objects. So I've been working on a tool for pop synth outputs. This is a Sankey diagram, which kind of helps you visualize, like how rare, first of all, it is to get a double compact object from a bunch of binaries, and where do we lose these systems? So yeah, the hope is to have this become a tool so you can input any simulation and kind of peek into what's happening to all of the systems. This is supposed to be interactive. I couldn't figure out how to embed it into the Google Slides, but you can also get the statistics of the rates of the different systems and what they go through. So yeah, I invite a transferring of knowledge and ideas, stable or unstable. Yeah.
This is super cool. And as a person who has a code, I just want to advertise that something that we should do with your tool is use the recently released bin codex format that Ruggiero helped lead the development of. And this is a uniform output code format for all population synthesis code. So everyone should be able in practice to convert your outputs so that we all can use each other's outputs. We've tested it in a Lisa code comparison project and it's working on 7 codes. So probably your
Great.
code maybe is in there, but also if it's not, we'd like to get it in there.
Very cool. Thank you for doing that.
More questions, thoughts, comments?
Yeah, I just want to ask, this is a really cool picture, cool plot. I'm wondering, the height of those shape is depends on some of your preliminary result. Let's say 50% of your population goes to stellar merger, from ZAMS, and another 50. I mean, if there's some population perspective,
Mm-hmm. Exactly, yeah. You can actually get those percentages in the interactive figure. This is just a screenshot. Yeah.
Cool. Right. Any more questions, comments? Otherwise, okay, one more.
What would be the error bars on these different snakes? If you say change the mass transfer efficiency or something?
So yeah, I'm not sure about that, but yeah, I want to pass through different models and see how much this kind of figure changes the statistics of it, and just also visually, because it gives a good picture generally to see.
Great. All right, thank you, Anna.
Thank you.
Up next, we have.
Please come to the front.
It's me and I forgot to put my name. Hi, so I'm Amanda. I'll put a name in there somewhere later. But okay, so I'm actually have a presentation on Wednesday, which is not about this. So I have 2 separate hats. So if you want to talk about BE stars, this is one of my hats. And one thing that I'm doing is SPH simulations of BE stars in binary systems. And I'm looking mostly at coplanar non-eccentric cases because now we have this SPH code and we can actually do a very much higher resolution simulations than what we could before. So the number of particles there is actually wrong. Don't look at that. And one thing that I'm very interested in is that, for the first time that we can actually simulate the system from beginning to end. So BE stars, if you're not familiar with them, they have a disk that forms from the star outwards. So I'm sure you're very familiar with systems that look like this, but BE systems, they go to that point, the matter around the system is actually coming from the central star. The central star is losing mass and is creating this whole structure around the system. And one thing that I'm very interested in is on the second plot there, we're actually looking at the companion. So this is the BE star, this is the companion. So we zoom in this guy, we get this guy. And I'm basically trying to show what the velocity of the particles is around this companion. And one very cool thing that we can see in this particular simulation, apparently we have something that is very similar to a Keplerian disk. But if I look at my other simulations, which I cannot put in one slide, we have some systems that are much more disturbed than this. So yeah, I have about 15 million plots that look like this for all my simulations. So if you want to look at that, I can show it to you as well.
Thank you. Questions, comments, thoughts?
I guess a comment regarding how this, for instance, post-interaction systems would be observed. I think one detail about this is that it can provide contamination to the strip star from its rapidly rotating companion. So that's something that has been suggested for a few systems observed, that they show weird abundances, perhaps not sufficient helium at the surface. So those things could potentially come from this.
Yeah, that's great.
So I think you said that in some simulations you don't see a disk.
I see something disk-like, maybe kind of elongated. It really depends on the viscosity that I have for the disk of the BE star, and also depends on how close the system is and all of that.
Okay.
So for some systems, like I have something that's kind of rotationally going around the companion, but kind of low.
Do you think it also might depend on the resolution? I mean, closer to the accretor, closer to the companion, would it become a disk, or do you think it's just not a disk in any scale?
It might be very close to the companion, but like there's only so much I can zoom in this kind of simulation, so I can't look super, super, super close.
What about cooling? And how do you treat it? Like the other
I do not.
I think that could play a big role in what you see.
Yeah, absolutely.
In terms of the structure. Yeah.
Yeah, for sure. But this is like, sadly, it's only like very simple simulations. I don't even know what the companion is in this case. I know it's something that has a mass. That's basically it.
Did you investigate what should be the minimum rotational velocity in order for the presence of the disk?
The minimum rotational velocity of which part of it exactly? Because I have a lot of things rotating in this.
Like, of the accretor you are showing of the equatorial.
Like how much the star itself is rotating? It's not. It just has mass. So I'm not really looking at it. I have a sync particle that is the companion. So I'm not treating that as a real star in this sort of simulation. Sadly, yeah.
All right. Thank you. And up next we have, I believe, calls for collaboration.
Yes, Floor. Hello. So I'm Floor Brookgarden. I show this plot. It's actually an interactive plot, but basically what you've already heard is that I'm interested in like gravitational wave sources, but a big question is how do they form? And a big question that's recently in the literature is, do most of the black hole mergers that we see today with LIGO, did they actually go through a common envelope phase or not, like their progenitors? And one thing I just did for fun is like, okay, there's been a lot of different simulations, different codes from population synthesis code, MESA, COMPASS, etc. What do those codes in the literature show? And this is actually what you get. So on the right panel, you actually see that actually most of the codes predict binary black hole rates that you could kind of say like, okay, 100% of binary black holes are formed from pairs of isolated stars. But then when you ask the question, okay, but did most of these stars go through a common envelope? You reach all the way from absolutely none of them in the bottom, where most of the bars are like orange, to like, yes, all of them basically went through a common envelope phase in the top panels. And so one thing I'm interested in is to understand these differences between the codes, why there's such a range. And so if you have one of those codes, like for instance, Sylvia Tunen is on the paper that's already included in here, please come to me. I would love to like involve you in like a quick fun paper that maybe discusses some of these like differences between simulations and codes. Thank you.
Questions?
Just want to ask, the Poseidon is V1 version, like do the solar metallicity? Like we could try V2, like
yeah, we'd love to.
All the metallicity.
Yeah, we'd love to.
So in your results, have you checked the many uncertainties, like including the critical mass ratio and also the supernova cake and also other aspects that what's the impact about
Yeah.
those things?
Yeah, so actually these are not only my simulations, but like things that are out there in the literature, and they like different simulations have different like critical mass ratios, like different gigs, different like stability criteria. They're actually, you cannot see it, but like if you zoom in, all these colors on the left are kind of a way to like visualize that. Again, would love to show this in more detail in person. And it's also interesting to see that sometimes even prescriptions with this like codes with some of the same assumptions, like say the same values for beta or alpha, like end up in very different areas in this plot, which of course is because there's other assumptions that they have different. But that's for instance things I would love to discuss. Like, do we expect the simulations to be on the like vertically in the space that they are, and can we explain why they are where they are? I would love to discuss that with people.
Thank you. All right, thank you. Next slide, I guess. Right.
Yes. Hi, this is me. I actually intended for this to be in the question section, so sorry about that. But I think this is a good thing to collaborate on, and I'm going to talk about this in quite a lot more detail tomorrow. But yeah, the question is, why are so many post-interaction binaries eccentric? And here we've got the orbital period on the x-axis, we have the eccentricity on the y-axis. This kind of blue contour is showing what the models predict the eccentricity distribution should be. All of these points show a variety of different observed systems, and the main thing is to take from this is that there are lots of different types of stars that are observed to have these high eccentricities at short orbital periods. And some of them are relatively early-ish, like the wide SDBs. These are a post-red giant branch star with a main sequence star, going all the way up to at least some systems containing white dwarfs. So I think that this is a problem kind of all the way through the evolution of the systems. And yeah, I'm going to talk about all of this a bit more tomorrow, and various ways that people have tried to solve this, and also ways that it has not yet been solved completely and satisfactorily. So yeah, I don't know if anyone has any questions particularly.
Thank you very much. So I actually also talk about this with Robert when I was visiting University of Cambridge. For example, for those observed objects, is there a way to classify them from those formed through stable mass transfer process and those after common envelope interaction?
So I think at least for most of these points, I think that these are mostly expected to be stable mass transfer, not common envelope systems. Even the subdwarf systems, these are stable mass transfer. And if you look at the orbital periods, these are orbital periods of like several hundred to several thousands of days. So this would be quite difficult to get through common envelope unless it was extremely efficient, I think. Yeah. Yeah.
Yeah, so I think this is like the canary in the coal mine for mass transfer when you have a AGB red giant.
Yeah.
And I'm wondering where's the analogous population in the higher mass systems? And I
Yeah,
think
sure.
maybe it's just because we don't have large enough numbers, but probably this is the same, going to happen again with massive stars.
I know of at least one system that was worked on by J.J. Eldridge in 2009, gamma squared velorum, that has a period of few hundred days, I don't remember, and an eccentricity that is significant. So they seem to exist also at higher masses.
Yeah.
There was also a question there. So, as we're waiting anyway, is that the only system that we know in the massive regime right now? That's post-massive. Well, that's why I'm
There's the neutron star. Gaia.
Yeah, Gaia, the H1.
Yeah.
There are some
Makes it more
eccentricities,
difficult,
they're
right?
larger.
The eccentricity could always go.
Discs.
Yeah, so circumbinary disks is one kind of proposed thing, but I don't know if all of these have circumbinary disks. And especially like, I don't know if the SDB systems have, I don't think that they have big observable circumbinary disks at least. I haven't worked too much on the mass transfer side of things, but I have done quite a bit of stuff from the tide side and also some stuff from the triple side. And I, at least personally, do not feel that I've resolved this problem. So that is what I'm hoping that maybe lots of people in this room can help with. Yeah.
Yeah, sorry if maybe this is repeating something we already said this morning, but I'm not sure I really follow the discussion then. So this mean that the sample that Natsuko found would fall into this same area, and so we have now maybe a few more thousand systems that would fall in the same area and cause the same problem?
It seems like it, I think. Yeah.
Okay.
I thought. Yeah, because you had systems that were kind of like these-ish periods and just generally across these eccentricities. Yeah.
I'll just add to that there's, for the more massive systems, people shouldn't worry that they're not in Gaia, because the Gaia DR3 astrometric binary data set that Natsuko's data is coming from effectively doesn't include any bright stellar companions above 5 solar masses because of an unfortunate cut that had to happen due to the Gaia scanning law. So they'll be in DR4, but we should not fear that, like, don't read into the fact that we only have BH1, BH2, NS1. Hundreds are coming probably. Yeah.
Great, thank you. Next slide.
I think, yeah, so, sorry. Yeah, I think Kritik put a lot more slides, which are really interesting, but because we're 10 minutes over time, I think we might call it a day. So maybe applause for everyone.